So in this video we will talk about the Wilson's theorem, which says that if a number p is prime, then if we take the factorial of p minus 1, then this is congruent to minus 1 modulo p. So in order to prove this, we have to start by proving another lemma kind of thing, which says that if x squared is congruent to 1 mod p, then x is either equal to 1 mod p or x is congruent to minus 1 mod p. Okay, so this is only valid if p is prime, if p is prime. Okay, so let's see what it means. So if we start with proof, so we have a proof here. So if x squared is congruent to 1 mod p, this means that p divides x squared minus 1, which means that p divides x minus 1 or x plus 1, which means p divides x minus 1 or p divides x plus 1. Note that we can only go from here to here because since p is prime. To appreciate that, let's assume that we have a prime number, let's say 7. So 7 divides a product of two numbers, maybe 35 times 3. Okay, now 7 divides one of them, right? It has to be a case that's the number which is the divisor, which divides one of the products if the divisor is a prime number. But as a counter example, let's say 8. Now 8 divides 10 times 12. Okay, now we know that 8 divides 120. This answer is what? This answer is 15. So 8 from 120 divided by 8 is 15. Okay, but 8 neither divides 10 nor divides 12. Okay, it so happens that this is the only case, the only reason is that 8 is not a prime. A factor of 8 divides 10 and another factor of 8 divides 12, and therefore 8 divides the product of these two numbers. But in terms of prime, it is mandatory that one of the products is divisible by the divisor here. Okay, now back to our situation. We say that x divides p divides x minus 1 or p divides x plus 1. So what does it mean? That x is congruent to 1 mod p by definition of modulo, or, and this guy means that x is congruent to minus 1 mod of p. Okay, so this is the first thing. Okay, now I want you to imagine that we have a prime p. Okay, and every number from every positive number from 1 to p minus 1 has an inverse modulo p. Now remember, what did we talk about inverses? Inverses are possible if the number which we are taking the modulo from is a prime number. Okay, now every number from 1 to p minus 1 has an inverse modulo p. Now the question is whether that inverse is unique or not. Now we already know that inverse of a number is always unique, but sometimes the inverse of a number is the number itself. So for example, if I say let's say 10 inverse modulo 11, this is equal to 10 again. Why? Because 10 times 10 is 100, and 100 if you divide by 11, because 10 times 10, this is 100, which is equal to 1 mod 11. Okay, so how many numbers are there from 1 to p minus 1 so that their inverse is themselves? Okay, in other words, what we are trying to say is that if I multiply a number by itself, if I have a number maybe a, and I multiply by itself, I get 1 modulo p, or a squared equal is congruent to 1 modulo p. Now this is exactly the lemma we proved before. So this is only always true if this is 1 modulo p, or this is equal to negative 1 modulo p. And can I say negative 1 as p minus 1? Yes, I can say that because it's modulo p, so I can add p to this number, and in terms of modular arithmetic, it will not change. Okay, so conclusion. So then from 1 to p minus 1, there are two numbers which are 1 and p minus 1 who have themselves as their inverse. So how many numbers are left? From 1 to p minus 1, we have p minus 1 numbers. Now two of them are already taken because they have themselves as their inverse. So then we have p minus 3 numbers. P minus 3 numbers, which means from 2 to p minus 2, have unique inverses. Or I can say there are p minus 3 divided by 2 pairs, so that the product of each pair is 1 modulo p. Okay. Now so much so for the build up. Now let's start with the left hand side of the theorem. Now we have p minus 1 factorial. This is equal to 1 times 2 times 3 times up to p minus 2 times p minus 1. Now what we are interested in? We are interested in modulo p product, right? Now from 2 to p minus 2, we have the answer 1 times 1 times 1 times 1. So how many ones are there? The number of pairs we have. So p minus 3 over 2 ones are there, and 1 times 1 times 1 is just 1. So we are left with 1 times p minus 1. Okay, so now this is mod p. Now then this we can say p minus 1 mod p, or we can say, actually this should be -1 mod p. So this is a very simple proof. So then the conclusion is that p minus 1 factorial, this is congruent to -1 mod p whenever p is prime. So this is the Wilson's theorem for you. Now what if you have a number, maybe k, and you check that k minus 1 factorial is not congruent to -1 modulo k. What can we conclude? We can conclude, so if this is the case, we can conclude that then k is composite. So in other words, k is not prime. So you can check, if you have a big number, you take a factorial and then check whether the remainder when you divide by k is k minus 1 or not, or -1 or not. Okay, so this is another check for checking whether a number is prime or not. Whether it's feasible or not, it's a different story. It depends on the machine and depends on the specific circumstances. Okay, so this is it about the Wilson's theorem. Hope it was easily understood and it was explained clearly. Thanks for watching. Hope you liked the video.